Your content today is the most important content for your test. What we learned today, if you are capable of doing this, you will do excellent on your test, okay? It's as simple as that. If you can't do today's lesson, you will do very, very poorly on the next test. It is the in terms of what we want to learn over the course of the year, you guys know how to take the derivative of 3x squared, right? You get 6x. Okay, you learned how to take derivatives. It's like, what's the next most important thing after that in calculus? Well, maybe the chain rule. Chain rule is finding derivatives as well. But this would be right in line with one of the most important pieces to learn, and it is this. The first derivative test. And that means when we take a first derivative, it tells us something about the function. If the first derivative is greater than 0, meaning it is positive, then the function is increasing. If the first derivative is less than 0, then it is negative, and the function is decreasing. So if the first derivative is positive, it's on its way up. If the first derivative is negative, it's on its way down. Local mins and local maxes, a little bit different. Right here, do I have a local max or a local min? I have a local max. What do you notice about the derivative at this spot? The derivative is equal to what? It's equal to 0, isn't it? Now, you said it's a local max. Prior to the local max, is the derivative positive or negative? It's positive, okay? It is on its way up. Afterwards, the derivative is negative. It's on its way down. And so you have a local max when the derivative changes from positive to negative. And if it changes from positive to negative, it must cross over what value? 0. So it changes from positive to negative, and f prime of x is equal to 0. You have a local min in this situation. Right here I have a local min, and you can see that the derivative at this spot is 0. Prior to it, the derivative is negative, and after it, the derivative is positive. So a local min occurs when f prime of x changes from negative to positive, and again, the derivative is equal to 0 at that spot. I should caution real quick here. I say f prime of x is equal to 0. If we had an absolute value function, there we change from negative to positive. We do have a local min there, and the derivative does not equal 0. So it's also possible that the derivative would not exist. But in most situations, we'll find that the derivative is equal to 0. But the true definition, we want to know changing from negative to positive. Okay? So we now have something new, and that is a second derivative test, and that tells us about something called concavity. Okay? Oh, okay. This is really the only kind of conceptual piece that's kind of tough to see today. If you can figure this part out, then you'll be good to go the rest of the way. I'm going to draw a tangent line here, and I'll draw another tangent line. And I'll draw another tangent line. Draw another one. And another one. Okay. As I move further towards the right, what do you notice is happening with those tangent lines? Yeah, they're going from positive to negative. Actually, the tangent lines, the slope of the tangent lines are decreasing, aren't they? And so you can see that the tip of the tangent line is continuing to drop further and further down. Even if I draw one right here, you can see again that it's dropping further and further down until maybe I get to a spot, say something, you know, maybe like that. That might be the most negative, right? And then I don't think I could draw a tangent line that's any steeper than that. That's negative. After that, if you notice, the tip of the tangent line starts to pick up again, doesn't it? And it kind of coincides with the shape of the graph. As you see here, the tip of the tangent lines are dropping here. But they're starting to pick up here. We call this concave down, as in it sheds water. If we were to dump water on it, it would shed water to either side. This is concave up, as in it would hold water. See the difference? And we say that it is concave up if the second derivative, so the rate of change of the first derivative, is positive. It's greater than 0. If f double prime of x is negative, then it is concave down. We talked about that one important spot right here where it seems like it switches from dropping to then going up. That's called your point of inflection. And the point of inflection is where f double prime of x changes from negative to positive, or where f double prime of x changes from positive to negative. So we don't discriminate between positive, negative, negative, positive with the inflection point. We don't care which one is happening, just as long as one happens. So, and yes, if it's switching from negative, positive, positive, negative, then the second derivative you'll find is equal to 0 in that scenario. Okay. All right. So one last piece before we try an example. Is this a local max or a local min? Is it concave up or concave down? Concave down. So local max will occur when it is concave down, or where the second derivative is less than 0. The local minimum will occur, as you can see here, I have a local minimum. Am I concave up or concave down? Concave up. So where the second derivative is positive, I'll have a local min. Okay, let's try a basic example. Says, for the following functions, identify intervals of increasing, decreasing, concave up, concave down. Also identify local max and local min and inflection points. So what I do is I set up my first derivative. What is the first derivative? X squared minus 4. Does that factor? Yeah, it does. It factors to x plus 2 times x minus 2. And that's going to make up my very first number line. I have a second derivative. What's f double prime of x? 2x. And that's going to make up my second number line. I'm going to plot the critical points where the derivative is equal to 0 or does not exist. I have negative 2 and I have positive 2. And for the second derivative, I have 0. Now, as you can see from our definitions, we're wondering where it's greater than 0, less than 0, so I'm wondering about inequalities. If you remember from last year, we solved these type of inequalities by simply plugging in points and testing them. So I'll plug in negative 3. Negative 3 plus 2 is negative. Negative 3 minus 2 is negative. Negative times a negative, positive. If I plug in 0, I get 2 times negative 2. That will give me a negative. If I plug in positive 3, I end up with a positive result. Here, if we punch in a negative number, we get a negative result, and a positive, we get a positive result. It's as simple as that to tell us some of the important characteristics. Namely, we are increasing over what intervals? Do I find out increasing from the first derivative or the second derivative? First derivative. So I'm increasing from negative infinity to negative 2, union with 2 to infinity. Yep, wherever the first derivative is positive. I'm decreasing from negative 2 to 2. If I want to talk about concavity, concave up and concave down, which derivative do I look at there? Second derivative. So I'm concave up from and concave down from negative infinity to 0. Tell me something about the local max. A local max happens when I change from positive to negative within the first derivative. So at what point do I change from positive to negative? Negative 2. And at what point do I change from negative to positive? Positive 2. So these are not intervals. These are actual points. I have an x value. How do I find the y value? Plug it into which one? The original. If I plug in negative 2 to the third is negative 8. So I have negative 8 thirds. This would be plus 8 or plus 24 thirds plus 6 thirds. 22 thirds, or 7 1/3. If we plug in positive 2, we get positive 8 thirds minus 24 thirds plus 6 thirds. So I have negative 16 thirds plus 6 thirds is negative 10 thirds. And the inflection point happens at inflection. Do I find that first derivative or second derivative? Where the second derivative changes sign, and that is at 0. So if I plug 0 in, I get 2. Now, here's part of what I love about this, is that you can then take this information, just as I have it right here, and you can put it on a graph. And all of a sudden, we can come up with super exact graphs. If I make this a positive 5 and this a positive 10, negative 5, negative 10. So I counted 2 right about there. I'm just going to plot some points and see that everything is verified by my testing. Yes. The inflection point I find by looking at the second derivative, where it changes from negative to positive or positive to negative. And that happens at 0. I take that 0 and I plug it back into the original. So I have an inflection point at 0, 2, which is approximately right here. I have a local minimum at 2 and negative 10 thirds, which is negative 3.3. I have a local max at negative 2 and positive 22 thirds, or 7 1/3. Those are 3 parts that I know. This is a local max, so it'll be concave down at that spot. The local min will be concave up. And you look at that, and right away you say, well, come on. We sketched that pretty quick. How accurate could that really be? If we go to our graph, we type in 1 over 3 x to the third power minus 4x plus 2, and we create a window where our x values are from -4 to +4, tick mark every one, and our y min, we go from -10 to +10, tick mark every 5. Again, this is what Newton would have done. And I think that that's a pretty exact graph. Go get some brain food. We'll see you in a bit. Before, if we check out this graph on the calculator, you know, I think Newton would have been very happy with that type of a graph. I mean, it's pretty exact. Note that this is the first time where we've been able to find the actual height of the local max and local min. So we're going to be able to be excellent curve sketching mathematicians. So here's what I want you to do. I want you to try B on your own. Go. YouTube, I just got the, you're going to make us try something on our own. And I say, but studies show that you learn more if you try it on your own. Oh, but we want you to do it. Studies show you learn less when I do it. Oh. Cite my source, me. Okay, so there's example 2 worked out. So you can see the intervals of increasing, decreasing, local max, local min, inflection, everything. Should be good to go. Let's do letter D. We're going to skip C. Let's do letter D. We'll start by listing off f prime of x. What's f prime of x? Does that factor? So we get -6 times x squared minus 7x minus 10. Does that factor? -5 and x plus 2. So, whoops, sorry. Oh, so did I not write this correctly? It would be better if it was a -60x, wouldn't it? So if it doesn't factor, then we have to leave it like that. So we have a -6 times x squared minus 7x minus 10. And as you said, it does not factor. So if it doesn't factor, what do we do? Quadratic formula. Somebody punch in quadratic formula. Tell me what we get. YouTube, Kevin Gens, 4 minutes, 2 seconds. Program. Who's got some decimals for me, folks? 8.22? 1.22? Thank you. Okay. So I've got those values. F double prime of x. -12. 12x plus 42. Can I figure out where that's equal to 0? Yeah, so -42 is equal to -12x. Divide by -12. And I get 7/2. Or 3.5. Okay, let's do some testing. What number would you like to test for the first derivative? -2. So remember, it's negative here. So -2 squared is 4 minus plus 14 is going to be 18 minus 10, 8, and then times -6 will be a negative. Plug in 0. Positive. Plug in 10, we get 100. Minus 70 is 30. Minus 10 is 20. Times negative is going to be negative. What number is easy to plug in down here? 0, we get a positive. And then plug in 4, and we get a negative. Wow, that was easy. Increasing, give me an interval. Awesome. Decreasing, give me an interval. Union with. Now I want to look at concavity. Which derivative do I look at for concavity? Second derivative. Concave up from infinity to 3.5. Concave down 3.5 to infinity. Do I have a local max? At what x value? (8.22). That's where the first derivative changes from positive to negative. So 8.22. I'm going to need a y value. So I'm going to go to y equals. I'm going to type in my original function. And up here, negative 2x to the third plus 21x squared plus 60x. I type in 8.22. I get 801.3. Local min at negative 1.22. Plug that in. Negative 38.3. And inflection point occurs at 3.5. I need a y value. 381. There we go. And I'm going to make a graph. I sure will. I'm doing 4 dashes for the y value. So I'm making my graph 10 by 800. If I plot the local max, 8.22, 801, be up here. The local min of negative 1.22, negative 38. Inflection point 3.5 and 381, so short of 400. And I know it is decreasing and concave up. Again, x min, I'm going to go to negative 10, positive 10, scale every 2. Y min of negative 820, max of positive 820. Tick marks every 200, and I press my graph. I guess maybe that end spot didn't look the best there, but it's pretty close. For your assignment, just 6 problems. 11 through 13, don't worry about sketching the graph. But for 29 through 31, please make sure that you do sketch the graph. I will give you a work day this week, but I need to finalize kind of how we're going to do this week first. So I'll let you know tomorrow when your work day will be.